Okay.
Alright, we're going to talk about series versus parallel. So, somebody made these in, like, who knows, the 80s, the 70s, I have no idea, because they were just here when I got here. But it's a really cool set of lights. I've got one for series and one for parallel. Okay? Alright, you guys with me over here? Yeah?
Yeah.
You ready? Okay, this is series. Alright, so we got our four bulbs. What do you notice about them?
They're equal. They're pretty equally lit.
Okay, they're equally bright. Somebody said they're not very bright.
That's
okay? And they're hooked up to the wall. So what's the total voltage of the circuit?
120.
120, that's right. Okay? And you guys have even measured the voltage of the wall to verify that.
Yeah.
Okay? Alright, now check this out.
Oh, Christmas lights.
Okay, okay, look at that. One goes out, they all go out. Okay, now, they're like the old Christmas lights. Okay, these ones that I've got strung up here, there's a bulb out right there. But the whole string doesn't go out. Okay? And that's because there's something called a shunt resistor. That's another resistor besides the filament that allows the current to pass by. Okay? And sometimes it's in the socket. It depends on the string of lights how that really works. It's not really important for today's discussion. But the old Christmas lights were a huge pain. Okay, have you guys seen that movie, The Grinch?
Yeah.
Doesn't the Grinch walk up to the Christmas tree, pull out one light bulb, and the whole tree shuts?
Yeah.
Okay, and then you'd have to go through the whole Christmas tree to figure out which bulb it is. Okay, each one depends on the other one. All right, that's a series circuit. Okay, sometimes we like series circuits. Sometimes we like things wired in parallel. Okay, today only series. We're going to kind of mention parallel, but we won't actually deal with it. Okay? All right, hang on.
Wait, no, I had a question about shunt resistor.
Okay, what?
So you said the shunt resistor kind of goes around it. Is it
Yeah.
just like a little bit of a higher resistance then? So that
But it doesn't light up.
Right.
It won't actually light up. It'll allow the current to pass. Okay? What the resistance is of that, I'm not exactly
Like
sure.
just this much higher? Or something?
It's yeah, you know what, to be honest, I don't know what the resistance of the shunt resistor would be. Okay. So anyway, we got our four here. All right, now notice this. These light bulbs are all the same. Okay? Their resistances are all the same too. Okay? Let's look at our note sheet. On our note sheet, I did it a little bit differently. Okay, I took this one, and because, just to make it a better example, I made the resistances different. But there's still four of them, and they're still all wired in series. This is how it looks in actual life. That's how it looks when we diagram it on paper. Okay? So I think there's a hole punch through your 6 volt. Oh, I didn't hole punch these. Perfect. It would have punched right through that. That's why I didn't do it, by the way. Not because I was slacking on hole punching. Course.
Absolutely. 100%.
Okay, so there is only one path for the current to take. That's the main thing we need to know about series. When we're dealing with circuits, this is our first circuit diagram right here. You guys know the symbols already, but we've never actually drawn a full diagram of an actual circuit. We like to draw equivalent circuits. So let's do that. We keep the battery the same, and then this is a simplification. We take the whole circuit and we draw it as just one resistor. Okay, we're simplifying it. Okay, now for series and parallel circuits, resistance, current, and voltage all have rules that we have to follow that go with each side of the paper here. Resistance in series is super easy to deal with. Okay? All we have to say is this. Resistance simply adds up. Okay? So on your equations page, there's an equation that looks like this. It says RS, that means the resistance for the entire series. Sometimes it's called REQ. What do you think EQ stands for? Equivalent, or R total, it might be said sometimes. Okay, that's equal to R1 plus R2 plus R3, and so on for as many resistors as we have. So you could have 20 resistors, and they would simply add up. Okay, so what's the equivalent resistance for this circuit? 10 ohms. 4 plus 3 plus 2 plus 1. So we put 10 ohms here. And that is going to be our R total. Okay? So as we go along here, we're going to fill in this chart that describes all of these values for everything in the circuit, including the total. So we just figured out that the total resistance is 10 ohms. And up here, we know our total voltage is 6 volts. Okay, so when we have 2, we can get the other one, right? Just using Ohm's law. So before we do the rule here, let's go over here and say I total is equal to V total over R total. And that's just Ohm's law. We've already done it like 30 times. So here we have 6 volts over 10 ohms, and we get 0.6 amps. Okay, and I can go over here, and for current, I can get 0.6. Okay, now how do we diagram current? We can diagram voltage in ohms, but what do we do with current?
Isn't it equal?
Okay, well, yeah, you're getting, that's kind of the next thing we're going to do. Okay, let's check this out. Current's flowing in the circles, in the circuit, so we usually just use an arrow. Alright? But on our diagram, remember current is the flow of positive charge. Okay, you guys remember that whole thing? The embarrassment to physics? Does positive charge actually flow?
No.
No. That's from the protons. The protons are staying there. It's the electrons that flow. Okay? But way back in the day they said, oh, hey, positive charge flows. So let's make current, conventional current, flow of positive charge. Okay? So we got to say which direction it's going sometimes. So which, on our diagram, is the little or the big line the positive? Big. This is positive. This is negative. So our current is going to flow in this direction, and we could call that I total.
I thought it flowed towards the positive.
Okay, it flows away from the positive and to the negative. You can think of it like this. All these positive charges, they want to go around and hang out with the negative charges. Okay? Positive and a negative attracted, right? So, and then really what's happening is the electrons in this side are going around the circuit to the positive side. Okay? But we actually diagram it the other way. I don't know why they haven't fixed that little problem. It'd be so easy to fix. It would be way easier to fix that than the United States fixing and going to the metric system. Okay? But they need to do it, okay? But they haven't done it. Okay, now on this drawing right here, let's go like this, and this is I total. And it's going to go around through this circuit. Okay? Before we get any more into current, let's measure some stuff. Okay? So we got our multimeter here, and we measure ohms when things are disconnected, so we'll take that off there. Let's unscrew a light bulb. Okay, now if there was bare wires here, I could attach these to those bare wires, but that's dangerous. Okay, we don't usually have bare wires on things that we plug into the wall, so we actually have to pull the light bulb out. Okay, any guesses on what the resistance is going to be for this thing?
0.5.
1 ohm. Okay, let's see.
4.6.
So I'm going to connect it here with the red, and I have to kind of hold that on with my thumb. And then I connect to the bottom of the light bulb. Okay, and we got, let's call it 35. So we got about 35 ohms. Alright? So what's the resistance of the entire circuit?
35 times 4.
Okay, it says 35 times 4. Do you guys agree? Okay, so let's check it out. Now how do I test the resistance of the whole thing?
Each end of
Left to
those
right.
prongs.
Okay, take the plug, we'll put that over here, and what is 35 times 4? What do we got? 140, sounds good. Okay, what do we get? Oh, we get 157. Okay, is it close?
Yeah.
Does physics actually work?
No.
Somewhat. Okay, now you see it's changing. Okay, this is kind of interesting. And the first time I did this, I plugged it in and I'm like, why does it keep going down? Okay? And then I kept thinking about it. What are these things doing right now? Well, they're not doing anything because they're not plugged in. You could say that, okay? But what are the filaments doing as time goes by?
Cooling down.
They're cooling down. Okay? Alright, and it turns out, we haven't really learned this yet, but for wires, which these are filaments, they're really just really thin wires. Okay? The colder they are, what happens to the resistance? It goes down. Okay? So extension cords that are really hot, we don't like that because we want the resistance to be low. Okay? So check this out. What are we at right now? 142? 141? Okay. Let's do this. Let's plug this in for a second. Okay, now what's happening to the filaments?
They're heating up.
Warming up.
Yep, they're warming up. Okay.
Well, why are the ohms dropping if you have no lower?
The ohms were dropping because they were cooling down. So as they cool, the resistance goes down. As they warm up, resistance is going to increase. So what were we at? 142?
Why were the ohms getting lower
The
though?
ohms is resistance.
The ohms were.
Oh.
The ohms
sorry.
is the unit for resistance.
Right.
Okay. So we're at 142 or 146.
142.
Okay. So let's pull this out and quickly connect. Oh, it doesn't like measuring the resistance very much because they're hot, okay?
The resistance
But eventually it
too
will once they cool enough. Yeah, I'm not getting very good values.
high. Is it like too high for it to read?
I think so.
Can you switch it to?
Oh, you know what? I'm over the, it's
Yeah.
because I'm not on the right scale. That's what's going on. Okay, so now it's come down below 200. I was on the 200 ohm scale. Alright? So I needed to be on the 2 kilo ohm scale right there. Okay, so you can see as time goes by, it's cooling off. Resistance of the whole circuit's going down. Okay, so that's kind of a cool thing to look at is the temperature aspect of this whole thing.
Probably like the electronics don't work well in heat or something.
Well,
Or
it
is that-
kind of depends on what we're talking about, okay? This is light bulbs specifically. When we start talking about those carbon compound resistors that you were using in class on Thursday, the temperature thing does not apply to those. Those stay constant temperature. Those don't heat up as much as a filament does. They heat up a little bit, but they don't heat up like a light bulb. Alright? Okay, so other rules we need to take a look at. The current for series is super easy as well. All we have to say is same everywhere.
So constant.
Okay, it's the same everywhere. Okay, and the reason is there's only one path. There's only one path for the current to follow. Okay, it's going to go down here, and it's it's going to go back around here. It's the same everywhere. Okay, now look at this. We're not going to really talk about this today, but here the current's coming down and then it meets a junction. Okay, and see how it divides all over the place? Okay, this is like a 1, 2, 3, 4 lane highway. Over here, this is like a 1 lane highway the whole way. Okay, there's no options. There's only one path. Okay, so if we're going to measure current, we use an ammeter, right?
Yeah.
What's the symbol for an ammeter?
Oh, A.
I hear crickets.
It's A, isn't it?
Okay, it's an A with a circle number, right? Okay, is that coming back to you guys?
Yeah.
So let's draw an ammeter right there. Let's draw one kind of in the middle here. And then let's draw one right next to the battery there. We could use this in any of the circuits we create in here. And if we connect this in series with the rest of the components, it's going to tell us current. Okay, so let's put some numbers here. 1, 2, 3. Which ammeter is going to give us the largest current?
1. Oh, shouldn't they all be equal?
Oh, trick question, huh? Thanks, Mr. Hicks. Okay, all same, right? Okay, but when people first look at this, probably when I first looked at this, I said, oh my gosh, look at this. Current has just left the battery. That's the most current, right? Okay, that's what we want to think. That's the common misconception. People think that current gets used up. Okay, batteries get used up. Okay, the current supply that they can provide, but as far as a snapshot in time, the current does not get used up. So it's coming around here, okay, but there's as much current here as there is here, and there's as much current here as there is here. Same everywhere. Okay, these two do not use up current, okay, and there's not less in this spot. Questions on that? Okay?
So, is there a way to like limit the current so much to where like if you just kept adding resistors at one point in the circuit it would be higher than at the other end? Like if you had an open-ended circuit.
Well, the definition of a circuit
Would be
is that it's a
complete.
loop.
Okay.
It's a closed loop that current can flow. If you don't have a closed loop, you don't have a circuit.
So it
Okay.
would work.
Now we could put really big resistors so virtually no current flowed.
Okay.
Okay. If I grab the ends of this battery right here, okay, is there some current going through me right now?
Yeah.
Okay, there is a little bit. Okay. Okay. Now if you lick it,
Yeah.
the resistance has gone down seriously, hasn't it? Okay, don't try that at home. Alright, that's what like 7th graders do for dares. You guys are way too mature for that kind of thing.
I dare you. Do it. Do it.
I'll lower myself.
I don't dog dare you.
Okay, now look at this. We can continue filling in our chart. 0.6, 0.6, 0.6. And you see how easy current is to deal with in series. Okay, now to voltage. Voltage is a little bit more complicated, but it's not going to be any big deal. Okay, now you guys know that I relate as much physics to rafting as I possibly can, right? So bear with me for a second. Hopefully this will help this make sense. Okay? So, let's say we're going to go on a rafting trip. And we're going to start up at some elevation up here. Okay? And then we're going to end, the river's going to drop. We're going to end at some elevation down here, which I could pull across and call elevation B. Okay? What type of energy is driving us and the water down the slope?
Gravity.
Potential.
Gravitational potential. Okay? And we are getting kinetic from that, right?
Yeah.
Okay. So, if we're going along here and the water's pretty flat, it's not going to drop very much. Okay? There's no rapids. A rapid's created by a big drop. right? Okay, so let's say we have a little rapid. Okay, we got a little drop in elevation. Okay, that'd be like going over the 29th Street Bridge or under it. Okay, there's a little rapid there. Okay, then we got some flat water. Then we drop a big rapid. Okay, let's say we go through one of the rapids on West Water down here. More of an elevation drop. It's going to be more exciting, right? And then let's say we go through a really big rapid. Okay, like Skull Rapid or something like that. Okay, big elevation loss. Okay, all right, now, why are we talking about this? Okay, what if I make this a circuit instead of a river? Okay?
Those resistors, little rapids.
Those are resistors. The rapids are the resistors, man.
Dang it, Emily.
Okay?
Don't feed
Good
the
job.
beast.
Now, instead of elevation driving water, we have what driving charge? Voltage. Okay? So, check this out. Here's a battery. You guys like that? Okay, here's the positive and the negative side. Okay? Let's say this is 6 volts. Okay? You guys see how all of the voltage is used up from here to here? It's just a diagram. It's not real. Okay? But which resistors are taking the most voltage?
Bigger ones.
Big resistors. Okay? The little resistors, so if I pull a line over like this, okay, do you guys see how this right here, delta V, is bigger than this delta V right here? Okay? Alright, it's like this is the voltage level of the battery. This one's taking the most. Okay, that's how it works in this circuit. So if we look at our notes here, which resistor is going to take most of the, or not most of it, but the most voltage?
From 4 ohm.
The 4 ohm. Okay? Then the 3 ohm, then the 2, then the 1. Okay? So here's how it works. We'll start out with something easier and then we'll get more complex.
So the numbers are the data values of the resistor. So technically speaking, the 4 ohm resistor draws less.
Well, that's what we're going to do right here. Can you see the board on that, Mitchell?
Yeah.
Okay. All right. Let's draw a really simple circuit. Okay. Let's say we've got the same battery. Okay. 6 volts. And we wire 2 resistors to it. That's not a resistor. That's just a bad wire. Okay. And let's say I make that 1 ohm and that 1 ohm. They're the same. Okay, how much voltage does each resistor get?
1.
Not quite. We have to use all the 6 volts.
3.
So they each get 3. Okay? Alright, let's say I take the 1 ohm resistors out and I put bigger resistors in there. I put 2 ohm resistors. Okay, how many volts does each one get?
3.
Same, 3 volts, right? Let's say I put 2 mega ohm resistors. They're each 2 million ohms. Could I do that?
No.
Yeah, they're out there. Okay, how much does each of those 2 mega ohm resistors get? 3 volts. Okay, easy.
Until you add a third resistor.
Okay, now let's say I put a, let's say I put a 10 ohm and a 20 ohm resistor in here. Okay, discuss amongst yourselves.
4, 2. Done.
Is it possible that the first resistor could take all of the voltage and the second one didn't?
Okay, that's a good question. Is it possible that the first resistor can take more because it's first in line? Okay, turns out if I switch these, you get the exact same answer that we're going to get in a second. It does not matter the order. That's kind of a big deal. Okay, just like on the river, it wouldn't matter which order those rapids were in, big or small first. You're still going to get the same elevation drop. Same thing here. Okay, so what's the total resistance of this circuit? 30 ohms. Okay, so this resistor is 10/30ths of the total, or 1/3, right? So it gets how much of the voltage?
1/3 of it.
1/3 of the total voltage. So 1/3 of 6 is what? 2 ohms, okay? This one is 20/30ths of the total. So it gets 2/3 of the voltage. So how much does it get? 4 ohms. Okay.
Wait, but
Let's do one more kind of to quiz ourselves, and I'm going to put one up here where you're going to need a calculator, okay? So, see if you can do this, and if you can, then we're doing pretty well.
Can we write anything down for voltage?
Yeah, we will. Okay, how much voltage does each get in the circuit? That's a 7 ohm and a 26 ohm and a 6 volt battery. Some of you don't have calculators out. Like going to Mordor without a sword, coming to physics without a calculator.
are we gonna get like decimals?
Yep. Gonna get some decimals.
Got it.
Okay, so what is my total resistance?
33.
Okay.
33.
Okay. So these can get us the percentage of the total, these ratios here. Alright? So 7/33 times 6 comes out to what?
4.72.
4.72.
1.72.
1.27.
Okay, let's round it to
1.3.
1.3. So this is going to get 1.3 volts. Okay, I just made this problem up, so I'm relying on you guys to give me accurate answers.
The other one is 4.72.
Okay, tell me what it is.
No, it's 3.7.
It's
4.7.
Can you even math?
Okay, 4.7 volts. Nice. Okay, now check this out. What do these add up to? 6. That's our check. Okay, do you guys see how the whole thing's been used?
Yeah.
Okay. Alright, so over here, let's say this. First thing is the total voltage has got to be used by the circuit. Okay? Okay, and then we can say that V total is divided proportional to the R values. That's the proportionality sign. Okay? In other words, bigger R values, more voltage use within the same circuit. If we're talking about resistors that are in the same circuit. Okay? Okay, so over here I just showed you how to figure it out, but there's another way too. Okay? So 2 ways. Okay, so let's split this up into 2 sides. Okay, here's the first way. That's using ratios. So the resistor that we're talking about, so R over the total, so let's say R total down here, times V total. Sometimes that's the most convenient way to do it, is using a ratio like that. Okay, the other way is simply to use Ohm's law. Okay, so we got V equals I times R. If we know the current and we know the resistor, we can just do V equals IR for that single resistor rather than for the whole circuit.
So we could do that for a circuit of lights because we know I is equal to 120.
Well, the voltage is the 120, not the current.
Okay.
We don't know the current. We could calculate the current of this, but we don't know it. Okay, we know the voltage. All right, so calculate all the voltages here. Using either method, it doesn't matter which one.
So a light bulb with more resistance, is it going to be like brighter or something?
Well, it depends on what we hook it up to. Depends on the voltage.
A light
Are we
bulb with
hooking up
higher
to a
resistance
battery?
will be brighter.
Okay, if the voltage source is staying the same, the more resistance we have, the less the current's going to be, right? So if the current goes down, the brightness is going to go down. Okay, let's check out the chart. I'll show you guys both ways. Okay, let's do ratio first. This is a 1 ohm resistor, so what's the ratio for it compared to the total?
0.6.
It's a tenth. Okay, so I'm going to do a tenth times 6, and I get 0.6. Okay, that's the ratio way. Alright, now since we know all the currents anyway, we can just multiply. So this is going to be 1.2. This is going to be 1.8. What?
It's not A.
Oh, thank you. I messed that up. I've been doing, yes. Okay, volts, volts, volts. Good. Okay. Now 2.4. Okay, what about the powers? What do I do for those?
P equals I.
Okay, you guys can do those on your own. They're just I times V. Alright, fill in the whole chart.
Power is watts.
Power is watts. Tomorrow we will do parallel.
Is that W?
Okay, good job.
Watts W.